Welcome back to AERO 1020, Theory of Flight, presentation number 23 on high-speed flight. This presentation will include an overview of air compressibility as it applies to the speed of sound, the definition of Mach number and critical Mach number, and shock waves and how they develop and the consequences. We'll also discuss wave drag, critical drag Mach number, and swept wings. Remember the presentation about the different types of airspeed and equivalent airspeed and how it really didn't apply to the aircraft that we're flying at this point in our careers because they can't fly at greater than 200 knots. And compressibility only applies to aircraft that can fly at high speeds of over 200 knots. Under 200 knots, the air is only marginally compressed. It doesn't really greatly affect aerodynamics. And at slower airspeeds, air behaves like a fluid. And as you may remember, Daniel Bernoulli studied fluid dynamics. Once we have the capability to fly at high speeds of over 200 knots, compressibility causes some problems. Air is compressed as it flows over and under the wing, which changes density, or rho, and this causes a large increase in parasite drag. In the 1940s, engineers discovered wave drag, and wave drag is a new type of parasite drag which was discovered to increase total drag when you are near Mach 1. Mach 1 is the speed of sound. It was thought that it would increase exponentially, which would create a sound barrier. However, that turned out to be untrue. Even back in the 40s, there were already man-made aircraft that could travel faster than the speed of sound. The Bell X-1 was piloted by Chuck Yeager and was the first aircraft to exceed the speed of sound in level flight. That flight occurred on October 14, 1947. Here's a link to an excellent video that you can watch about the history and the development of the Bell X-1. You can find this link in the content section of D2L under optional videos. It's important to remember that the speed of sound, or Mach 1, is just a reference point. Sound waves are pressure waves. The sound waves that we hear move in all directions, not just in one direction. Another important point about Mach 1, or the speed of sound, is that it is affected by temperature. Mach 1 actually increases as the temperature increases. As you can see in this table, at sea level and 59 degrees Fahrenheit, which is standard temperature for sea level, the speed of sound is 761 miles per hour. At 20,000 feet, at minus 12 degrees Fahrenheit, the speed of sound goes down to 707 miles per hour. And at 40,000 feet, at minus 70 degrees Fahrenheit, the speed of sound is actually over 100 miles per hour less than the speed of sound at sea level. At 40,000 feet and minus 70 degrees Fahrenheit, the speed of sound is 660 miles per hour. There are three broad classifications for the speed of sound. Speeds of less than Mach 1, or less than the speed of sound, are known as subsonic. Mach 1, or the speed of sound, is known as sonic, and greater than Mach 1 is supersonic. We can refine the classifications even further to subsonic, transonic, supersonic, and hypersonic. Speeds of less than 0.8 Mach are subsonic. From 0.8 to 1.2 Mach is transonic, and from 1.2 to 5.0 Mach is supersonic. Any airspeed greater than 5.0 Mach is known as hypersonic. The difference between subsonic speeds and sonic and supersonic speeds is that air can get out of the way from in front of the airfoil when it's traveling through the air at subsonic speeds. The pressure disturbance can be transmitted ahead of the wing, which actually prepares it to go over and under the wing. In sonic and supersonic flight, because the air no longer has time to move out of the way in front of the airfoil, we have shock waves. So how do shock waves develop? Well, to understand this, let's go back to subsonic flight. Remember the positive pressure bubble at the leading edge of the wing called the stagnation point? Well, near Mach 1, the stagnation point no longer exists, and the air is no longer rooted around the top and the lower surface of the wings by the bubble. Here's a figure showing an airfoil at subsonic speeds, and you can see that the direction of flow of the air actually changes before it even gets to the airfoil. As an aircraft approaches Mach 1, or the speed of sound, the air no longer has time to get out of the way before the wing passes through it. So pressure disturbances at subsonic flow can travel in all directions, but when you're at or above Mach 1, they can't go forward anymore. The aircraft is going too fast. The barrier between subsonic flow and supersonic or sonic flow gets very distinct, and it's called a shock wave. When shock waves begin to develop, they greatly increase drag. This drag is a new parasite drag called wave drag. Another important term to define is critical Mach number. If you observe the flow of air over an airfoil, you know that the speed of the flow is accelerated faster than the forward speed of the aircraft. So the air moving over the wing is actually flowing faster than the true airspeed of the aircraft. At or above a certain true airspeed known as the critical Mach number, a certain segment of the air over the wing is traveling at supersonic speeds. In this figure are two airfoils, A and B. Airfoil A is traveling through the air at 0.7 Mach, and airfoil B is traveling at 0.85 Mach. The velocity of air flowing over airfoil A is not quite at Mach 1, or the speed of sound. However, the velocity of air flowing over airfoil B is just reaching the speed of sound, or Mach 1. So 0.85 Mach for this airfoil is the critical Mach number. Notice the velocity of the air flowing over the wing actually slows down after it reaches Mach 1 near the trailing edge of the airfoil. When the flow of air over the airfoil is accelerated above Mach 1 and then decelerated back below Mach 1, a shock wave develops, and this shock wave creates what's called wave drag. As the aircraft continues to accelerate toward Mach 1, the supersonic flow region becomes larger on the upper surface, and you can even get a shock wave forming on the lower surface of the wing. As the aircraft gets closer to Mach 1, both of the shock waves move aft toward the trailing edge of the wing, and both surfaces, upper and lower surfaces, experience supersonic airflow. When the aircraft reaches speeds of greater than Mach 1, a shock wave actually appears ahead of the airfoil, and this is called a bow wave. These shock waves create additional drag known as wave drag, and wave drag removes kinetic energy from the air. At a certain true airspeed, this drag starts to increase exponentially, and that airspeed is known as the critical drag Mach number. In this figure you see a graph that shows the drag coefficient increasing after the critical Mach number, but then increasing even more above the critical drag Mach number. Now, reaching the speed of sound, or Mach 1, requires a huge amount of thrust. Propeller planes are limited by the speed of the propeller tips, so a pure turbojet aircraft is what is required, or a rocket-propelled aircraft is required to achieve supersonic flight. Now, we can mitigate the effects of wave drag by sweeping the wings back on a supersonic aircraft. The swept wing creates more span-wise flow of air instead of chord-wise flow, and that slows down the speed of acceleration over the top of the airfoil. Since we slow down the chord-wise flow of air over a swept wing, the lift generated is less than the lift generated by a straight wing. But in high-speed flight, we're not really concerned about lift. We're more concerned about drag. The increase in drag matters more than the decrease in lift when we're talking about swept wings used in high-speed flight. This graph shows the coefficient of lift for two different wings. One is a straight wing and one is a swept wing at different angles of attack. And you can see the coefficient of lift is much greater for the straight wing. So when designing a glider, would you use a swept wing or a straight wing? If your objective is to design an aircraft that will maximize lift and minimize drag, you would use a straight wing rather than a swept wing. Here are some links to some good videos about supersonic flight. You can find these links in the content section of D2L under optional videos. That's the end of presentation number 23 on high-speed flight. In our next presentation, which is the last presentation of the class, we'll review canards.